In this video, we will talking about the work of force, the principle of work and engine and energy uh, of the particles. So we starting with work and energy. Okay, another equation for working kinetics problem involving particles can be derived by integrating the equation of motion F equal to ma with respect to displacement by substituting at equal to v dv by ds into ft equal to mat. The result is integrated to yield an equation known as the principle of work and energy. This principle is useful for solving problems that involve force, velocity, and displacement. This can also be used to explore the concept of power. Okay, to use this principle, we should understand how to calculate the work of force. Okay, according to previous slide. Okay, we found that the work and energy principle actually is come from the Newton's second law, and then after we integrate this equation in combination with the kinematics equation that we change the term of ADS to be VdV. And after we integrate this term, we obtain the principle of work and energy like this. Okay, that is useful for the problem that related with force, displacement, and velocity. If our problem is that we related to this parameter force, displacement, and velocity, we should consider uh, the work and energy principle to solve the problem. For work of a force does work on a particle when the particles undergoes a displacement along the line of action of the force. Work is defined as the products of force and displacement components acting in the same direction. So if the angle between the force and displacement vector is theta, the increment of work du done by the force is defined by du equal to F ds cosine theta. By using the definition of the dot product or the scalar product, that is change this product change the vector quantity to be the scalar one. Okay, and integrating the total work can be written as the work done from first position to second position is equal to the integration of the force vector scalar product with the small quantity of the displacement vector, that is the position vector, that is dr. Okay, from the first position to second position. According to this, if F is a function of position, that is the work done is become after the scalar product. We have the work done from the first position to second position to be integration of F cosine theta ds from S1 to S2. And if both F and theta are constant, okay, so this equation is simplified to the work done from first to second position is become FC, that is for the case that force is constant and theta is constant. Okay, so it's become F cosine theta times the difference in position, that is S2 minus S1. And we have to know that work is positive if the force and movement are in the same direction. And if they are opposite, and if they are opposing, the work is negative. And if the force and displacement directions are perpendicular, the work is zero. So let's take a look for a particular case that is the work of a weight. Okay, the work done by the gravitational force acting on the particle or weight of an object can be calculated by using these term. Also by the force is become weight, and it is negative because the weight is always downward. Okay, is always downward, and if we set up dy to be up at the positive, so then the work done by weight is become minus weight times the change in vertical direction. So according to this equation, the work of weight is the product of the magnitude of particle weight and its vertical displacement. And then if delta y or vertical displacement is upward, the work is negative. And if the change in vertical displacement is downward, the work done is become positive. Okay, so let's consider work of a spring force. Okay, if we consider the spring and we have the mass attached to the spring like this. Okay, when stretched, a linear elastic spring develop a force of magnitude Fs equal to Ks, where K is the spring stiffness and S is the displacement from the unstretched position. The work done of the spring force for the case that we consider the spring. We have the applied force to the spring. Okay, and for this case, the spring and the displacement is go in the same direction. The force applied to the spring. Okay, force applied to the spring. So the work of the spring force moving from position S1 to S2 is become integration of Fs ds from S1 to S2. But force acting to the spring is equal to Ks. So then the work done applied to the spring is become 0.5 Ks square minus 0.5 Ks1 square. That is the positive. But actually, normally when we consider the spring force, we normally consider at the body that attached to the spring, for the body that attached to the spring. So then the work done on the particles that is attached to the spring, the force Fs exert on the particle is opposite to that exert on the spring. Okay, so the work done on the particle by the spring force is negative to the above value. Okay, so then if we consider the body instead, the particle instead, we see that when the particles is moving to this direction, okay, the spring force is always opposite to the displacement. Okay, so then the work done on the spring is always negative for this case. Okay, so the if you consider this picture instead, for the case that we consider the work of spring to on the particles. Okay, the negative mean the spring force acting to the ball is opposite to the displacement of the ball. Okay, and we have the work done from position 1 to position 2 is become like this, that is a negative value of a half k s2 square minus s1 square. Okay, and we have to note that s1 and s2 are measured from the reference point at s equal to 0. Okay, so then so it is important to note the following about spring force. The equation above are for linear spring only. Okay, that is we consider F equal to Ks. Okay, and if it is not the nonlinear spring, okay, we may have to substitute the force function into the integration term and integrate it to obtain the work done. Okay, the work of spring is not just spring force time distance. That is, we normally found out for the case that work done is equal to F dot S, and most students uh, always get the trap that they substitute the work of the spring to be Ks and time the displacement. Okay, time the displacement directly. That is not correct, because for this case, the spring force is not constant. So then this term is not correct. We have to determine the work done by the integration of F ds. Okay, so and I substitute F as the function of S into this term. Okay, and be concerned the sign of the spring force after calculating it. Okay, it is positive work if the force pull on the object by the spring and the movement are in the same direction. Okay, so then let's moving to the principle of work and energy. By integrating the equation of motion that we also have this term and substitute at equal to mv dv by ds, the principle of work and energy can be written as summation of the work done from position 1 to position 2 is equal to a half mv2 square minus a half mv1 square. That is, we define this term as the kinetic energy. So then we can rewrite this equation into this form. That is, we define this equation as the principle of work and energy. It's composed of the kinetic energy as the first position plus the work done from the first to the second position is become the kinetic energy at the final position. Okay, and we have to know that this equation is not a vector equation. Okay, so this equation is in scalar value, and both kinetic energy and work have the same unit. Okay, in SI unit, the unit of energy is joule, that is Newton meter. Okay, but in US customary unit or FPS system, unit are foot pounds. Okay, the principle of work and energy cannot be used in general to determine force direct normal to the part. Okay, since this force do no work. Okay, so for the case that we have the force normal to the part, it has no work. Okay, and the principle of work and energy can also be applied to a system of particles by summing the kinetic energies of all particles in the system and the work done due to all force acting on the system. And if we consider the work of the friction caused by sliding, okay, so for this case, when an object slides on the surface, the work done by friction force is equal to mu kn times s, and it is negative. Okay, however, we have to know that it is not the exact work done by the frictional force. The exact one is mu kn s palm. That is the s palm and s is maybe not equal. So as we know from static that actually the friction when we consider the small part of the contact surface, we will see that the friction force is the combination of the small value for the it is a summation of each uh, reaction force that is acting along each contact surface, and S palm and S is maybe not equivalent. Okay, so then the exact total work, it should be equal to mu kn times S palm. That is not exact to S. Okay, and the additional term should be the heat loss active occur when the particle is sliding on on the lab surface. Okay, we normally found that it has a heat also. So for this case, we can consider this term is maybe reasonable because it's composed of two terms, that is mu kn s palm and heat. Okay, so for in general to solve the problem with friction, we can apply this term for consider the friction force due to sliding. Okay, that is mu kns. Okay, that is maybe reasonable for work energy principle also. Okay, so then after this we will consider the example for the case of work in energy principle in next video.